Querying by location.
Good morning. Nice seeing you here.
See you. There's going to be a talk here, right?
Yes, there is. In 1 minute's time. I'm Jerry.
By me, I hope.
Fantastic. Christian, great to meet you.
You're not Ava.
No, Ava was the first thing this morning. Or not first thing this morning, it was like
Sorry?
half 10.
Oh, what are you talking about?
I'm talking about teaching programming to chemistry undergraduate students.
Cool. Change your schedule.
At some point,
So, yeah, hi.
herpetologist.
A few things from my side. Could you plan all these names?
Yeah, no, I had the moment where I asked every question.
Who was giving that talk?
No,
Yes.
right,
Yes.
yes.
If you are questions, I'm happy to
Fantastic. What involvement would you like me to have? Would you like me to introduce you? Would you like to introduce yourself? I'll introduce you. Andrew McCluskey introducing programming to undergraduate chemists. I will be sat there.
Okay.
I will have 5 minutes. Do you want the 5 minute sign with time for questions? Or as in you want it? So 25 minutes total.
Yeah, so give it 20 minutes. Because that's when I'm thinking, I haven't practiced it, it's like 10 minutes long. So that, if I'm running over that, when I'm great.
And what would be great is if you could just give me a thumbs up or something.
Yeah, I'll give it a nod. I'll try. I'll probably end up not like, I'll probably end up going, oh yeah, cool, great. I'm good. Grab my coffee cup, at least close it over so that it doesn't dissipate all the heat.
No, I guess think about later, but I'm just playing some
It's 14:31. Chances are like people will be trading still
Yeah,
after
it's
lunch,
fine.
but that's good.
Do you want to start with
Hello and welcome everyone to this is unamped, isn't it? You're not hearing it. Yeah.
There's a
Hello.
switch at the bottom perhaps?
Yep.
I thought that wasn't.
Hello. No. Are you okay to project?
Yeah, as everyone can, no one has a hearing loop or anything.
Well, the microphone is important for the audio.
Yes.
Oh, and the camera.
For the recording, yeah.
Press
The
hold.
other day, someone was saying if you hear the speakers, do actually hear it, but otherwise you don't.
Hello. There we go. Fantastic. Right. Hello and welcome to Andrew McCluskey's talk on introducing programming to undergraduate chemists. Thank you.
Oh. Alright, okay, this is going to be fun. I'm not used to doing this like a pop star, so we'll see how this goes. So I'm Andrew, but first things first. So this link at the top, this is a totally interactive presentation. You can go on that link and you can click things, and you can, there's literature examples, and there's links to notebooks, and my binder links, and all that. You can go and click on things, it's fun. Or if you can't see it, because I'm funny when I choose colours for things, so if it's something you can't see, you might be able to see it better if you go to the link. It's up to you whether you do that or not, but it's all there. So I'm Andrew McCluskey. I am a chemistry PhD student at the University of Bath. I also tutor physical chemistry to first year undergraduate chemists, and I am a demonstrator in the undergraduate computational chemistry lab at the Department of Chemistry in Bath. So I have a lot of different hats on, and I'm going to talk about some of the stuff that we've been doing in Bath to try and bring programming, and in particular Python programming, to the undergraduate chemistry course at Bath. And so this is all part of what's called the Python and Chemistry project, which I'll tell you some about. I have social media things. You can follow me, you can email me, I don't really mind. If you follow me on Twitter, it's mostly just me probably arguing with politicians about science policy. So, as we heard from Spencer's talk earlier on today, he studied chemistry and he didn't know how to program until recently. Chemists aren't typically taught to program. We go through our chemistry degree being taught how to do things like this. We get taught to mix our vessels, wear our safety specs and wear our lab coats, look at microscopes and all that. And nowadays more and more people are expecting chemists to do things a bit more like this, where they do seedy things and make drugs like the guy out of Breaking Bad. The fact of it is it's a lot more common nowadays for chemists be doing something like this. And this is actually what I do day to day. I'm a computational chemist. I use computers to do chemistry, basically. And this is happening more and more as chemistry has become more and more an analytical subject and a subject about data science, or data analysis. And so chemists are actually doing more and more data analysis. This is a plot of the percentage of academic chemistry publications that mention the phrase data analysis. So we're now at the case in 2008 where almost 40 or about 40% of all academic chemistry publications from all areas of chemistry, from organic chemistry, physical chemistry, anything, mention some form of data analysis. And they're not just analysing data, they're doing it in Python. So this is another plot that's the same thing, the percentage of chemistry publications that mention Python. And so now we can see how exponential this curve has got, and we're now at the case that 7% of all chemistry publications are mentioning Python. Now, I'm talking about academic chemistry publications, but people don't go to uni really to become academics. Academic people that are studying for PhDs and stuff like that like to pretend that they do. They like to pretend that we're training undergraduates to then go on and be academics like ourselves. We're not. We're training them to enter the industry. And now if we look at the Royal Society of Chemistry's employability page about chemistry, so the Royal Society of Chemistry is chemistry's learning body, and we see there's this mark right here, IT and technology, and this specifically mentions that in a chemistry undergraduate degree, you will gain experience and understanding of computer software models and processing data, doing this data analysis. And so this all kind of builds, so I ended up teaching myself to program in my spare time while I was working in industry. Well, my spare time, I automated half my job. And so it gets, the fact that we're not teaching chemists to program necessarily kind of makes me annoyed. It kind of winds me up, and when you speak to senior academics that kind of shrug off the idea of chemists programming, it makes me feel like this little person. And so, in an effort to counteract this problem where we're not training chemists to analyse data efficiently, we're getting using things like Excel. We started the Python Chemistry project, and so that was a project that started at the University of Bath Department of Chemistry by Drs. Ben Morgan and Fiona Dickinson about 2 years ago now. This started simply as putting Python into undergraduate lab exercises. So it was 2 years ago we got a Python lab exercise. And then over this past year, I've actually taken that and I started using Python as a teaching tool in my undergraduate physical chemistry tutorials. We then have also been developing bits of software, bits of teaching software to use in the undergraduate lectures, labs, whatever. They're all based in Python, they're all open source. And then we've also got a web page that overarches all. And I'm going to tell you all, this is basically what my talk's about. I'll talk about this Python chemistry project. So, starting off with the labs. Originally what Bath had one data analysis lab for your whole undergraduate in chemistry. And you did it in Excel. You got given a data set, and you were told to use Solver to plot some line and then figure out some numbers. That's now been overhauled. It was taken out 2 years ago and replaced with a Python data analysis introductory lab. Now it's the case, we're in our third year of the project, and there is 2 Python labs at each of first and second year of the student's undergraduate. So those cover an introductory basics Python lab, then there's an introduction to data analysis lab, and then there's 2 labs where they actually model chemically relevant data using Python. And so the way that we actually do this is it's all in a Jupyter notebook. I assume that everyone's kind of familiar with this sort of thing. So I'm getting a head shake. Okay.
Yes, I think it'd be worthwhile just briefly introduce.
Cool, that's fine. It's interactive, guys. So Jupyter Notebook is quite a common thing for myself and as a kind of research chemist, but it allows us to put markdown, so textual information, in alongside the code blocks, and it creates it so that students can actually have a self-led exercise. So in the way that a traditional laboratory exercise would work is the students would read from a book, then go away and mix their chemicals. Now what the students can do is read from a book and write their code. So it means that this can run as a typical lab would, where they just have a couple of floating demonstrators like myself that go about and go, the student sticks up their hand and goes, I've got this big error message, and I go, oh, it's because your 2 strings are different lengths, or whatever. So this is the way that we do it all. It's actually, we're now in the position where we're starting to open source all of the labs. So all of the labs will be available on the Python Chemistry.org webpage. At the moment, you can get the introduction to data analysis lab on that webpage, and you can go and have a look with it. I've actually now got it where I go to traditional academic conferences, I talk to people about programming, and they're like, oh, but where do I start? And I'm like, well, is your undergraduate chemistry? Like, are you a chemist by training? And they're like, yeah. And I'm like, well, go look at these resources. They're developed by Ben Morgan, who's an academic in Bath. They're worth their salt. Go check them out, and they'll give you the jumping off point that you need to actually use Python in your own work. We're currently working on a paper for the Journal of Open Source Education, which I'll mention again later on. It's if you're developing teaching tools, programmatic teaching tools, it's a very useful thing to get some sort of accreditation for what you've done or to get people to hear about it, especially in the spheres that I run in academic spheres where it's a kind of publish or perish mentality, which is in front of the case. So this is what I'm a demonstrator in the course, and this is what I get from a lot of the students. I will sit there, and I'll go over and I'm like, oh, so how you finding it? They're like, I signed up for a chemistry degree. I didn't sign up to do this. I'm meant to be a chemist, not a programmer. Why are you making me do this? To which my response is always, I have an undergraduate master's degree in chemistry, and I'm now doing a PhD in chemistry, and this is all I do. And then I also remind them about the employability statistics for people that can code versus people that can't. Almost all of them are like, all right, okay, fine, we'll go with it. So this is actually some feedback that we took after the labs. So this is just a word cloud of all the words. The first time I did this, that word useful was like twice as, or like a bit bigger, and I was like, hang on. There's about 9 times when I was putting in the data that said not useful. So that includes the negations. This includes the negations now. So that is a true useful. So we've got feedback off the students after the labs for both the first and the second year, and the fact that word useful is pretty big. Makes me feel quite good about what we've been doing. So that's looking at the kind of lab stuff. So the next aspect was bringing it into the tutorials. So these are small groups, 6 people and a PhD student, or 6 people in an academic tutorials. And I tutor physical chemistry, which is the borderline between chemistry and physics. So it is mathematically intensive. And now the University of Bath is slightly unusual in that it will accept people for a chemistry degree if they don't have A-level maths. There's only about 5 universities in the country that do that, and Bath is one of them. And so that means a lot of the time when you're trying to get physical chemistry concepts across to students, they don't have the mathematical underpinnings to keep up. And this is something I noticed over the past my first 2 years of being a tutor, and so I was thinking about ways to improve this. And I liked the Jupyter Notebooks framework, where it was quite interactive and the students would be able to see what's happening. I was like, well, maybe if I bring that in, the fact that programming means that I have to be completely explicit about the maths that I'm doing, maybe that can, through some sort of way, help the students. And now, I should know, I'm not trying to teach the students how to code during these tutorials. That is too much work for a tutorial. I'm trying to use it as a teaching tool and make it available to them in the future. The other benefit, of course, is that by having a Jupyter Notebook, and after each tutorial, I'll make one Jupyter Notebook for the whole tutorial and put that on a resource called My Binder, which is interactive, and the students can go access the resource after the fact, work through the tutorial in their own time, cover the concepts that they haven't been familiar with, that they haven't felt comfortable with during the tutorial. And that offers the ability of giving the students instantaneous feedback that may not be there during the tutorial. So I've actually got an example, which is always risky business when you're doing like a talk to have like live coding examples, but we'll see how it goes. So this is actually a question from our first year physical chemistry tutorial. You don't need to know the chemistry. The point of it is that you get these numbers and you plot them as a straight line, and the gradient of that straight line is equal to a mass. You can also determine that mass from this chemical formula. That's the 2 things that you need to know for this. So what we do is, this is actually how we bring it on in the tutorial. We have, obviously we're importing matplotlib and packages like curve fit in order to fit our straight line. And then I've got a function of the straight line which returns the gradient. This second cell will actually calculate the mass based on that chemical formula. So that's the mass that we should be getting from the straight line. And so we calculate this and we find that the mass should be 46 grams. This second cell will take all this experimental data up here and plot it and fit a straight line to it. So you can see where we fit a straight line. Sorry, I've just realised that this needs to be a 6 to make a point. So we fit in a straight line, and you can see that if you can make it out, it might be a bit fuzzy. So this is the real mass. This is the mass from the chemistry, is 46 grams. But if you fit this straight line, it comes out as 54 grams, which is quite a big deviation. And now all of my students would, before they came to the tutorial, all the good ones that cared, before they came to the tutorial, would work through the question using a pen and paper. They wouldn't draw the graph, because it takes a lot of effort for a student to draw a graph or go and use Excel or whatever. And I was like, well, what did you get? And they were like, oh, well, it was a bit big, but I think it's just a mistake. I think it's a mistake with the question. And I was like, all right, okay, well, let's plot it. We plot it, and I said, well, what to you looks funny about that curve? And now the teaching point is that once we get to the higher values of density, the model that we're fitting with this straight line falls down and doesn't work anymore. And so all the students went, well, now that you plot it, the line's not straight. Because you can see here the line does actually curve and is clearly tending towards being a bit more logarithmic or something. And I was like, yeah, that's the point. So what can we do? And they were like, well, let's consider fewer data points. Cool. And so the way that I've actually written the notebook means that we've got this variable data points up here. And so we can change this from 6, which is all the data points, to the value that was suggested in the answers from the academic that set the question, which is 3. So we can consider just those 3 data points, and we get a mass of 48.7 grams compared to 46 grams. That's a lot better. That's a lot closer to the value. And I was like, right, okay, done and dusted, question answered. You guys all know what you're doing now. And one student goes, hang on, this data point, that's already below the line. Is the model already collapsing at that density? I was like, I don't know. I've only worked through this based on Gareth's answers. Let's find out. And so I'm actually going to go in and change the number of data points we're considering just to the first 2. And we plot it again. The line doesn't appear to change that much, but our value actually reduces by almost an entire gram. And we get closer again to the real value. And so the point I'm trying to make with this example is just that the fact that we had this available to us in the tutorial environment meant that the students could interact with it, get that instantaneous feedback, and it kind of engaged them a wee bit more. You can see all my tabs I've got open. So I gave you kind of more formalised feedback for the labs. This is my informal feedback from doing the tutorial. So the students did appear anecdotally more engaged. They seemed to enjoy the fact that they could interact with the material through the Jupyter notebook. There was one particular industrious student who would go on to the resource that was available, go on and download the notebook after the tutorial, and work through it again. And then any time they encountered a problem or didn't understand something, they would modify the notebook such that it reproduced their misunderstanding effectively, and would send me that notebook. For me to be like, all right, okay, well, I'll understand where you're going wrong now. In the same way that when we're trying to submit bugs, we have to submit an example of how that bug is created, that student was doing that same process. And I think that's a win on all parts for me. Okay, so that's labs, that's tutorials. Now I'm going to tell you about the open source tools. So Bath, uniquely in the country, has undergraduate computational chemistry laboratory exercises from first year. No other university, no other chemistry department does that. And one of the things that we needed was what's called a molecular dynamics or Monte Carlo simulation engine, right? So this is time for the actual chemistry. Please don't leave. Please don't leave. So this is all the background you need to know. In chemistry, in computational chemistry, we can use a simulation technique called molecular dynamics. Molecular dynamics we can treat our particles as little balls that bounce off each other. When the density of those little balls is really low, we're effectively simulating a gas. And that's what you get here whenever the sparsely populated, they're not interacting much. As you increase the density, not to such an extent that it becomes ordered, so the particles are closer together, but there's no order in the system. You get a liquid, like water. And then if you increase it again, you'll get a solid where things crystallize. So things form an ordered pattern, and they're very close together. And using molecular dynamics, you can simulate these systems at different temperatures. That's all the chemistry you need to know. And so this led to us developing what's called Pylage. So that stands for Python Leonard-Jones. And Leonard-Jones is the technique that we use to simulate this. This is a completely open source Python library that's aimed to engage undergraduate chemistry, and also I've used it in graduate courses as well, students with this atomistic simulation techniques. It's under an MIT license, it's open source, it's all on GitHub. And we actually published in this Journal of Open Source Education about it, so you can go and, if you're really interested, you can read the paper, there's a DOI and everything. And one of the cool things was I presented this, I took a poster to an internal Bath HPC symposium, because I hadn't done any real HPC work over the past year, so I was like, I'll show people this. And a postdoctoral research associate came up to me from the physics department. He was like, well done, you've embarrassed the physics department. And I was like, why? He was like, because we should have done this first. So he came over and I talked him through the code and stuff like that. He's like, right, okay, this looks cool. So he forked the code on GitHub and then took my code base and wrote Python, which is a Python Ising model, which is something that's very common in physics undergraduates. And so he was actually able to it took him like a day's work to implement an Ising model within the same code base. So that was quite a cool result. So I'm going to show you, this is the logo for Pylage, which I'm really proud of. Because this looks like an L, but it's actually a Leonard Jones function. I know this means nothing to a lot of people, but it means something to me. I'm really cheesing with it. Right, so I can show you an example of Pylage. So Pylage, as it's a Python module, we import it. And now this is scary to chemists, but this is just a molecular dynamics algorithm. And this is actually something that we're now teaching in the undergraduate lab, in the third year undergraduate lab, where we're making use of this code. So the students are able to build up a molecular dynamics algorithm during the lab. So we're going to define this function that is an algorithm, and then we can run the simulation. And so now we can see our little particles bouncing off each other. And now from those pictures I showed you earlier on, can someone tell me what this is? A solid, liquid, or a gas?
Gas.
Oh, yeah, okay. It's a liquid. It's between a gas and a liquid. Do you want to see? I'll give you a real gas. When the particles, because there the particles are interacting quite a lot. Here, there's maths that you can do to show it. Here we've got something that's a bit more gaseous, and then we can go to a really high density and push our particles really close together, and we can simulate a solid. But you see the particles are still moving about because this is all being done at room temperature. This is effectively at room temperature of these simulations. And then because this is all a Python module, it's basically everything gets dumped into one class. So at the end of it, the students can take the information and they can plot it. So for example, this is a plot of the pressure with respect to the simulation time step. So you see the pressure starts really low, really high, when the system's not well equilibrated, and then over time it equilibrates, and you can see that it's going through equilibration. Eventually this will become really, really steady. Cool. So, if you are keen, you can go and try this out. Now, it runs on a MyBinder, which is, as far as I can tell, GitHub resource. So it's pretty slow, but you can also download it. It's on pip. You can. There's also a whole bunch of examples on GitHub. You can go and play with it. This is just these are examples of stuff. So you can also do like the dynamic. So you can also do Monte Carlo with it if you're interested. So the last thing I'm going to say is we have the web pages. The web pages are basically a way for us to advertise what we're doing. That's what it started out as. But since then, I started doing some blogs about basic Python skills, trying to put them in chemical context. So there's things like functions, where I've got a function that does an ideal gas equation, which is a common in first year undergraduate chemistry. And we've also started putting on information about applications of chemistry and applications of Python in chemical research. So at the moment, I'm actually writing a publication that all of the data analysis is done reproducibly using Python. So my plan, once I publish that, is to put a blog up on the Python chemistry webpage that shows people that this paper is entirely written in Python for all intents and purposes. This is what it looks like. I'm very proud of that, using Jekyll that time. And now I just need to acknowledge people who let me come here. So Ben, if you want to